So Mr. Pfeiffer is already sharing his screen. So he is the next speaker. He is the managing director of the Embedded Systems Academy, a company providing, among others, CANopen protocol stacks. And furthermore, Mr. Pfeiffer is in-person chairman of the CiA special purpose cars add-on devices. So, Mr. Pfeiffer, please overtake. Stage is yours.
Yes. Quick sound check. Do you hear me all right?
Yes.
Okay, thank you. Yeah, so my name is Olaf Pfeiffer from the Embedded Systems Academy. And in the next half an hour, I'll talk to you about applications and markets, and not only about applications and markets, but also what is required to get into these applications and markets. So if you're considering building a CiA 447 device or gateway, then here are a few hints on the things you need to observe. Just allow me a brief history of the Embedded Systems Academy here. So we are an active member of the CiA 447 users group right from the founding in 2007. And we contributed quite a bit, not only in these meetings, but also by developing code that later has been published for everyone to use, like the LSS fast scan cycle, which was later adopted into the 305 document. And we also enhanced it with a 29-bit feedback. So some of the gateways out there can do an even faster process in assigning these dynamic node ID numbers when these 29-bit feedbacks are used. So really from the layer setting services and the finding the nodes, we came down to a few 200 milliseconds to identifying single nodes here. We have implementations available since 2010 for devices, gateways, and I'll be also talking about some of the coprocessor solutions. And there are quite a list of test tools that we were involved in, because as you saw from Thilo's presentation, there are quite a few things that are different to the regular CANopen. So when it comes to testing, monitoring, analyzing, regular CANopen tools can only be used to a certain limit unless they implement the 447 specifics. So there's quite some work involved in getting these test tools working. Let's review some of the applications. We have seen those also from Thilo, but really the main drive behind 447, and I think in quantity, is both the emergency response and taxi applications. So in emergency response, that's everything that makes light and noise or sound. We also have the connection to the radio system so that you can communicate. And in taxis, of course, there's primarily the meter, but also there's a roof bar. We have also printer and potentially radio. Now, some of the not so often used markets are that we have the controls for drivers with a disability. So these include connecting remote controls for various lights, signals, horns, and so on. However, these are really very low quantities, but are something that some of the 447 gateways can provide. And also quite some implementations have some aftermarket add-ons. So we have seen 447 in use in fleet management for telematics. So it's really just your regular passenger car, but providing the telematic information required for some of the telematic systems then comes out of a 447 gateway. On the same line, we have the accident recorders, so continuous data recording in the background, and personally, a quite interesting, also low quantity market is armored cars. We have really seen some armored cars out there that came to the limit of the 16 nodes by CiA 447 because they have so many additional I/O modules in each door or video cameras and so on that you quickly reach the limit of 16 nodes. So let's have a look at the gateways first. What are your options today on gateways? The gateway, of course, is the most important thing in the car, because really you can't operate any 447 network without having a gateway. So today, the implementations that we see are either directly provided by the manufacturer. So you can go to your provider of your vehicle and ask them, hey, can you provide me a 447 gateway, please? And these roughly look like the diagram here. So what they all have in common, that somewhere on one side, here on the right side, they have the 447 port. So this implements the gateway side of the 447. So all the network management, node detecting, layer setting services that Thilo mentioned earlier. And this is where all the 447 devices get connected. And then on the other side, we have one or sometimes multiple CAN interfaces that connect to the internal vehicle networks. And these collect and provide the data that come from the vehicle. And we see here in the middle the symbol of a firewall, because really when you talk to the car manufacturers, then quite often you'll notice they do not really refer to it as a gateway, but some of them actually refer to it as a firewall. Yeah, because simply their primary interest, of course, is to make sure that although they provide access and provide data, it's also a firewall into their system. They don't want that someone from the 447 size can do unauthorized things on the internal vehicle networks. And this really is one of the biggest challenges in 447 and comparing different implementations is how much of the data can actually go both ways here. As you can see, the selected data here shows that it can go from right to left and vice versa. However, in very many implementations these days in gateways is really more, this is a one-way street where the car provides data to 447, but what goes back into the car is either close to zero or really just minimal and selected. This is unfortunate, because initially this went so far in some of the first implementations we have seen that data that going back could do things like writing something on your dashboard display. So a radio could show that it has push to talk pushed somewhere in an indication on the dashboard. And this is something lately that went away and is not used so often anymore. Well, these are the manufacturer-provided gateways. On the other side, we have the generic gateways. So the generic gateways are gateways that are not only for one specific car manufacturer or model, but they can be connected generically. And this is typically done by really connecting I/O lines to things like the ignition status, light status, horn status, and so on. And having an additional CAN interface here is optional. And if it's implemented, then it's really just for one-way receive only. So the model down here looks slightly different. Again, to the right, we have our 447 side and the gateway side. But on the left side, it could be without a CAN port. It could be just discrete I/O lines. So the I/O lines connected, and a CAN interface can be optional. And then typically that's also one way. And so here the firewall functionality is really no longer part directly of the device. The so to speak firewall is really more implemented depending on which signals we connect, because simply what we don't connect, we can't meddle with. And so data that is not connected cannot be manipulated. So this is about gateway implementations. The gateways that we know of are available with some of the car manufacturers. This is ordered by time. As far as I'm aware, Daimler was the first one to offer a 447 gateway, primarily for their taxi market initially. Then came VW and Audi, which has 447 gateways available in some of their models. Then Opel, as it was still part of GM, was using 447 gateways. Now with the transfer to PSA, I haven't seen any official statement or anything from PSA what they'll be doing in the future with 447. And same goes for Vauxhall, which is not mentioned here, but Vauxhall also had in the past, as it belonged to GM, quite a bit of usage for 447 gateways. And then there's BMW. When it comes to the generic gateway, then in association with our partner Peak, we have a generic gateway available. There's no size comparison here, but this is, well, bad example, but the only thing that currently comes to mind is a box of cigarettes. So this is maybe the size of 2 boxes of cigarettes, the small ones. And it has only one connector. This is not the specified CiA 447 connector, because on here there is a lot of discrete I/O additional pins, and there is additional CAN and LIN interfaces. So this can be programmed quite flexible to support a number of different vehicles. After we looked at the gateways, let's now look at some of the devices out there. When it comes to devices, we already said the probably biggest number of manufacturers you'll find in this department. By my counting, we must be worldwide now up to 6 or even more suppliers of blue lights, displays, and sirens that have 447 implementations available. And for taxi, there was metering was one of the implementations. And here's an example of a meter integrated into the mirror. So somewhere up here is the display, and really here the nice thing to have a standardized CAN interface minimizes the number of lines that need to be brought forward here towards the taxi. And then, of course, there are a few manufacturers that provide various generic I/Os. So this could be buttons and switches, dialers and rotary dialers. We also have seen video surveillance equipment. With the video equipment, please keep in mind that, of course, via 447, we are not really presenting any live data from video data because that's far too much data. The video cameras that have a 447 connection primarily use it for control. So enable, disable, start recording, stop recording, things like that. And then, of course, we have various diagnostic devices like a long-term data recorder in networks for later analysis, and various diagnostic software and hardware. Now, if you want to implement such a device and join these suppliers of 447 devices or gateways, then there are a few things you need to be aware of. Let's assume you already have a device that has a microcontroller unit which has a CAN interface, and this way you are just requiring a little bit of software to integrate into your system. However, this little bit of software is already so big that some of the older microcontrollers, and literally we have seen some of the first implementations of 447 were still done on 8-bit microcontrollers, but I really hope these days are over by now. So there are quite a bit of resources even in comparison to regular CANopen implementations. So we can see from our own code that in comparison to a standard 301 CANopen implementation, we require quite a bit more of RAM and buffers, where a regular 301 CANopen implementation can probably get away with a few hundred bytes of RAM. In CiA 447, we really need a few thousand bytes of RAM because simply we need to be able to buffer communication to potentially 15 other devices. And the dynamic node ID assignment also has quite a few things that need to be stored. So within your application, roughly the diagram will look like this. So you have a 447 task running, which somewhere has the object dictionary that is implemented and maybe has some non-volatile memory storage for some of the configurations. And then you have your task running with the real application that your device needs to implement. So if I summarize the challenges that in comparison to a regular CANopen implementation you have, then really quite a challenge is the wake up and sleep mechanism, because that is really 447 specific. It's not implemented elsewhere in CANopen. And the car manufacturers actually require that everyone has their own specifications there. I know some say you have to consume less than 1 milliamp when you are sleeping. Others require even less. So you really have to put your device into some deep sleep mechanism. However, still be able to wake up from the CAN network if communication starts again. And because the wake up cycle can be quite long. If something changed in the network or is behaving oddly, then the gateway really has to ping each and every device and see if it's still there and comes up. So this can go really in a few hundred milliseconds if nothing changed in the system. But if there's a single node that boots up too slow, because maybe there's somewhere Linux or Windows PC behind it, or something which is not permanently connected, then the power up cycle can easily extend to several seconds. And that is not really acceptable in all applications. So if you imagine a police car and you're already sitting in the car making a break, and now you have to go out on a mission, and you press the button to switch on the blue light. Well, if that is the first action and the entire bus is asleep, then if everything goes well, then it can happen that within a few hundred milliseconds your blue light goes on. But in worst case, if, as I said, one of these delays is there, a slower node, or nodes are not permanently present, suddenly such a startup could go 2, 3 or more seconds. And that's, of course, then irritating. So there's quite a few things that have to be considered. And it's interesting to see that the car manufacturers sometimes have different approaches on how to best deal with it. I've seen one car manufacturer actually do a sleep delay time of 2 hours. So really, it took 2 hours for the entire system to go back to sleep. And I think their thinking was, well, with 2 hours, we cover every break that a policeman or somebody else could do with the vehicle. And if they need it, it will be instantaneously usable again. There's no boot up cycle. So there is, as I said, quite different approaches how to deal with it. Then we already mentioned the dynamic node ID assignment using the layer setting services. The challenging part here is that to not further delay the entire process, your device, if you're building a 447 device participating here, really needs to be responding to CAN messages on the network within 10 milliseconds. Now, for deeply embedded systems, 10 milliseconds is not a problem. However, if, as I said, this is a more complex device with lots of tasks and potentially even running some Linux on top of it, then these 10 milliseconds become a challenge. So really, you have to look at your hardware and software layout if such response times are possible. And the last implementation challenge here to the right, the full SDO mesh. Here also, it's not about handling the requests that come in. Well, theoretically, although this is mostly theoretical, but it is possible that all 60 nodes, well, if I'm one of them, then all other 50 nodes more or less simultaneously send me an SDO request and want some data from me. And it's not too theoretical, because after a boot up and startup, typically every node starts scanning the network to find their partners. So there'll be a lot of requests. Who are you? Who are you? Who are you? And so your system needs to be able to handle these devices, even if they come in mostly back to back, meaning theoretically they could come in, let's say, within 20 milliseconds or 30 milliseconds, and then you have to have receive buffers big enough that you can process all of these and really ensure that you reply to each of them. Therefore, one of the earlier adoptions we did specifically for systems that are a little slower in startup and so on, like anything with a graphical user interface, Linux or Windows based, we said, well, the best way to still participate in 447 without any delays is using a coprocessor. And the idea here is that the coprocessor implements the entire 447 functionality in a separate communication chip, and the communication towards the host app, the Linux, Windows, or whatever system, is done using a regular serial interface. And now suddenly this becomes a single standalone running microcontroller unit, and all these challenges that I just mentioned are no longer a challenge towards the host, because the challenge is completely handled by the coprocessor. So even if this host app is has a boot up time of several seconds because there's an operating system booting here to the left, well, right after power on, if the configuration is already stored here in this coprocessor, it can reply to 447 requests on the CAN side and start immediately running and working. So the coprocessor solution is really a nice option we see used in specifically for devices that I said have graphical user interfaces and complex operating systems, non-real-time operating systems running. And of course, the resources now required on the host side are less, because literally this is also a filter towards the host, and it doesn't bother the host with things that it doesn't need to deal with. Here, just a few examples of coprocessor versions we did in the past. So either just the chip alone, we have worked with NXP or STM-based microcontrollers here. Then we also have a solution for a Raspberry Pi. So this is the Kenshinberry. It directly plugs onto a Raspberry Pi and can be used on that. Quite nifty for various testing and quick adoptions. And then we've also used from Peak one of their serial to CAN converter boards and modules that can act as such a coprocessor. Let's take a step now towards diagnostic. So when you start developing these devices, you definitely at some point need to do some diagnostics. So what are your options there? Well, with some of these handheld devices, they are also hardware provided by Peak system. You can do live diagnostic. So the live analysis is shows you the typical functionality. What are the detected devices that are currently operating and what is their overall status? So it's a little small here on the display, but literally just gives you the node ID number. The green light says it's operational, and the bar graph gives you an indication about how much it communicates. A heartbeat is okay, response time is okay, and overall traffic load is okay. And here we see the shortcut for the virtual devices, IVN gateway. This should be roof bar light, roof bar sound, and things like that. So you have a quick overview of what's going on. But also on some of the more advanced displays, we have then detailed timing, min and max values. So what is the minimum and maximum values each device had? Or you can also have a look at the overall bus load of your system and determine if you ever have a problem because you're hitting too close to the 100%. Here's an advanced example of live diagnostic data. So really, you need an overview like this to go in the details and see what's happening. So there's pick a few examples here. There's a current heartbeat time. What is the current heartbeat time? Then we have somewhere the below is the min and maximum heartbeat time ever managed. How many PDOs, how many SDOs do nodes produce? And so this gives you an overview. If there's a single node communicating too much or taking too much of the bandwidth, you will see in such a display. Very useful and really specifically originally written for this purpose. When we started debugging 447 applications, as you know how it is with bugs, they do not occur always, they occur sometimes. And if somebody reports you, oh, this vehicle has a problem once or twice per day in an 8-hour shift, well, the only chance you have is logging all data and then look at the data. And literally, we came to the limits of Excel, where you, I think, have only a maximum of 1 million lines. So my partner Andy wrote the Logzamina software, which does an automatic analysis of log files, and they can be of any length. They can be concatenated or in portions. So we have done automated log file analysis of log files collecting more than a week of data. And the nice thing is it will then immediately point out in red and highlight lines and find things where you had aborts, where somebody stopped responding, where heartbeats were lost, and things like that. So we can double check if the wake up and sleep works perfectly, see the devices participating, and it will find message losses. So if somebody does not reply to an SDO request, things like that will be measured, displayed, and analyzed. So we'll see for a device what was their minimum and maximum heartbeat time, what was their minimum and maximum response time to SDOs, and how much overall traffic did a device cause. And we can have this listed for each and every device.